Our speaker today is Dr. Chris Hughes. Chris is a research associate who oversees the day-to-day data quality of the DEOS network. Chris has also developed many of the quality control algorithms and systems we use, which he'll discuss in his presentation today. Chris joined CEMA back in 2014. Before joining CEMA, Chris completed his doctorate in our department's PhD in climatology program, where he conducted research on the sea breeze circulation in Delaware. The title of Chris's talk today is Beneath the Data, the Art and Science of QA/QC within the Delaware Environmental Observing System. And with that, Chris, over to you.
Right. Good afternoon, everybody. I'm Chris. Kevin just gave me the really great intro. So I'll talk to you today about our QA/QC procedures for the DEOS network. So first, let's look at a different slide. This is the same intro slide with the title, but as you can see, there are a bunch of things wrong with it. There's misspellings, some of the text is off center, some of the text here is tilted slightly, the color scheme isn't the best, and there's lots of problems. So some of these problems would be called automatically with spell check. Others, you'd have to look at it for a second and realize that some of the problems are a little more hidden. But either way, these issues highlight how important both automated and manual quality control processes are everywhere for catching and fixing mistakes before they become bigger issues. So with that, let's begin with the talk. So specific to meteorology, here are several examples of where sensor issues led to problems that made headlines in the news. The key here is to look at the word delayed. So in several of these titles, there's delayed, delayed, delayed. Also incorrect, 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 faulty. And these are words that are very common throughout. And these delays can be disastrous to emergency managers and the general public alike. While many of the issues here were caught and addressed, take a second to think about the issues that maybe we never caught and are still out there, and they're cracks in the data, and they're just treated as real and accurate at this point. So that's why it's crucial to identify these problems immediately and to be sure before taking action. So let's start with some definitions to ensure that we're all on the same page. QA, or quality assurance, is the process where we ensure that everything is set up correctly from the start, that sensors are properly installed, that equipment is calibrated, and we're fully prepared to collect accurate data. In our network, QC, or quality control, involves checking the collected data for errors, looking for sensor malfunctions, and sensibly flagging problematic data. Together, QA and QC are essential for maintaining the accuracy and reliability of all of the data that we provide. While this process seems straightforward, unexpected issues happen more often than we'd like. And as you can see in this image, that station, as Dave mentioned at the last talk, was hit by tumbling bleachers. That's something you would never expect in a million years, but it happened. So I'll start with a summary of the DEOS network. As mentioned, it was launched back in 2004. We have over 50 active meteorological stations and over 40 pond stations, all collecting data with well over 10 parameters. All of this data goes through rigorous QC processes, which I will discuss in the future slides. But over time, this has led to over 100 million data points in our network, and assuring the quality of this data is a crucial step that keeps the network functioning. And you can see an image here of our state, our region. We include Chester County up in Pennsylvania. Okay, I will briefly talk about the quality assurance processes before focusing on QC for the rest of the talk. It all starts with location. If we place a sensor under a tree, we will surely see distorted wind and rainfall measurements. While we do our best to have good station placement, it's always going to be challenges based off of getting permission and just finding spots that are just perfect. So there's always going to be issues, but we do the best we can, and we have a lot of stations. So we also have a lot of issues. We conduct routine quarterly maintenance to help make sure everything is working smoothly. We calibrate sensors so that they don't start producing inaccurate readings. We have SOPs for installing and maintaining equipment, and it's a lot of equipment. For example, we don't want to have an upside down wind sensor. That would obviously give us horrible readings. But seriously, we want to assure that the wind sensor is in the right orientation, or everything could be off by 90 degrees. And that might be hard to catch initially and could lead to some issues. We also document everything, or at least we try to. Documentation's key. It ensures consistency and gives us a reference point if something does go wrong. The field app, which was developed to help organize the documentation, field images, sensor histories, and other field activities, is a very useful tool that we use almost every day. In the end, it's all about making sure that from the moment the data is collected, it's reliable and that we anything that does come up. So this is a top level representation of how QC is integrated into our system in real time. And it's a very complicated image, but the idea is that there's several paths that the data follow and ultimately end up with a flag. And the flag could be good, it could be bad, and I will talk about that more later as well. It's really important to see that it does go through all of this, and it's a lot of data points. So let's talk first about the flagging system. In our flagging system, every point is assigned a flag. Preliminary flag would mean that no QC checks have been run. So that's kind of like at the instant that the data is measured. Immediately, we have some checks, and the flag can go from preliminary to good, to suspect, or bad. In the case of suspect, that would be where it failed a test, and we're not sure. We need to look at it. It's flagged for manual review. But if it's something that's just crazy, 1,000-degree air temperature, that's going to immediately be flagged as bad. And that's important to note because that means it's going to be immediately removed from our website and removed from our front-facing applications. And so I'll start with the level 0 check. So level 0 just means this is done first. It's the first line of defense, and it happens immediately after the data is recorded. So I'll talk about all of these, but we start with a battery check. We need to make sure that the voltage is fine, because if the voltage is low, then we cannot necessarily trust the reading or the value that's provided. This could happen any time of year, but usually it starts to show up in colder conditions when there's limited sunlight. After that, we do a range check to ensure that the values are realistic. For example, if we had a pressure sensor showing something like 500 millibars, that's never going to happen. At least I certainly hope not. But if it did, that could be representative of just the offset within the sensor, and clearly it's not right and should never be shown. We also flag extreme but feasible values. So in this case, I am showing a pressure of 970 millibars. Is that going to happen? Most likely not, but it could if there was a really strong low pressure over the region. So when we see something like that, that data point receives the suspect data flag. And in that case, we will inspect it. And from there, we can make the determination whether to promote the data to good or to put it in bad. Finally, if any maintenance is happening, we have a door open sensor that is triggered within the control box, the control panel at the station. So immediately, if the door is open, all data collected will be marked as suspect. And that's because something could be going on. If you're dealing with a temperature relative humidity sensor and you're holding on to it, it may bump that temperature up several degrees. And that's something that we can look for and note. And if we notice something like that, we'll flag that data as bad. But generally, the data will be passed off as good, as most of the parameters are not affected. So here's an example of data flagged as suspect during site maintenance. By flagging this data, we ensure it's manually reviewed, again, as I just mentioned. In this case, this was air temperature at Ellendale, and there's nothing wrong with that data, the 3 kind of yellowish orange points, and it was treated as good, and no further action was needed in this case. However, here's an example of a full temperature relative humidity sensor failure. From a QC technician's viewpoint, we see where the bad values started, but it is important to verify that the data before that time period was reasonable. So in this case, it was a functioning sensor, and then just out of nowhere, it went kaput. So in this case, no further actions actually needed on our end. QC detected the failure and flagged it perfectly. However, we will use our field app and address the issue, document the issue, and then eventually the sensor will be replaced. But from a flagging sense, QC took care of everything. I'll move on now to level 1 checks. So these are checks that are a little bit more involved. They require more data, a little bit more processing, and we just do this once a day in the early morning hours. They include spatial comparisons where we compare readings from nearby stations. For example, if most stations in an area were reporting 70 degrees, but one station out of nowhere was reporting 90 degrees, then that would require further inspection. It could be fine, it might not be fine. We also perform other tests such as a jump test, which flags for sudden immediate changes in the consecutive 5-minute values. That one's tricky because it happens often, and it can happen due to things such as the sea breeze or a thunderstorm. So a lot of times that data is good, but that can be indicative of a sensor that is having problems. Another test that we do is a minimum variability check, which helps identify sensor issues that might be a little bit less obvious. A special case of this test is what we call the frozen wind sensor check that specifically targets consecutive 0 wind speed values that last for hours in the presence of freezing conditions. So let's look at a few examples of these. So here's a case, again, with a temperature relative humidity sensor, but this is the temperature here. It looks pretty normal, and then in the late afternoon, early evening hours, we're just seeing jumpiness all over the place. And that's what triggered the jump test and probably also a spatial comparison test. And we looked back and analyzed this data and found that this was happening kind of frequently in the days before and days after, and decided to flag the whole chunk of data and report the issue. Here's a case of the failed jump test due to heavy rainfall. So in this case, the data is completely fine, but the temperature just went from, let's say, almost 80, 81 degrees, quickly down to 71 in 5 minutes, and then went down more after that. But we looked and verified that there were no issues, and that was due to a thunderstorm happening. Going to the next one. Here we call it a solar radiation issue at White Clay with the help of the minimum variability check. So as you can see, many of the values were 0, and the signature looked significantly different than the corresponding station during these 3 days. So over here in the green is the at the ag farm, the solar radiation, and this was White Clay. And you see there's missing values, there's a lot of 0 values, it just doesn't look right. While it's easy to see when I do this comparison here, it's helpful for us to have tests like this running in the background so that it's going through everything and can help point out issues that we may have. Here's another case of the frozen wind sensor at Townsend. Wind sensors that show 0 for a long extended period of time, especially when other nearby stations are showing wind, which was verified in this case, kind of really highlight the fact that this station had a frozen sensor and just had the wind speed, it was just frozen for a while. And then as the temperature warmed up, which we also verified, then it became unfrozen and then the wind speed resumed. We typically see a few events like this each winter season, and they last from a few hours. In this case, it's over maybe about 12 hours, up to 36, and they can impact between 1 and up to 10 stations, depending on the severity of the event. All right, moving on. So if you've noticed, I have not mentioned anything about rainfall, and that's because it's difficult. I'd like to focus on that now. So data from our tipping buckets, which we use to measure rainfall, is some of the most challenging to quality control. Rain is sporadic. It can occur with different intensities ranging from a light drizzle to an extremely heavy downpour. Also, some rainfall events are spatially consistent, but others are not, especially with convective events. And we can see large differences over a very small region. The tipping mechanism can get clogged or stuck due to the variability of the environment, or also for mechanical reasons. So as you can see from the slide, there's a strong likelihood that the bird did something. We don't know what it did, but it probably did something, and that tipping bucket is probably clogged. So Dave, you should probably check into that. So how do we recognize these clogs? Well, first, of course, we need a rainfall event. Otherwise, everything's going to look the same. In the case of a functioning tipping bucket, we would expect rainfall of varying amounts over each 5-minute interval, as seen in the first chart here in the green. In this chart, we see some data with 1/100th of an inch of rainfall in 5 minutes, which I'm pointing to, some with 2, some with 3. It's just a lot of variability, and 1 5-minute interval of fairly heavy rainfall. However, if there's a partial clog, as in the second image here, then it'll take rainfall significantly longer to work its way through, and it'll primarily be based on the volume of water inside the funnel as well as how clogged it is. But this generally results in this certain signature that is repeated hundreds of times. We've seen it all over the place when we have these clogs. And it's the single tip, this pattern that kind of spaces out with time and keeps going, and eventually everything tips through. Finally, a full clog, it's simple. No water is getting through the tipper and we're not recording anything. So what can we do about that? Well, we've developed an in-house clog detection system that can be used for real-time and also historical review of data. This system uses spatial comparisons to detect potential clogs in the network and provides flexibility by analyzing data over a range of 1 to 7 days. And that's important because some rainfall events can linger. Some can linger for multiple days, and we need more data to really look and see what it's telling us. Due to the complexity, rainfall is typically handled completely separately from the other parameters. It's also important to note that some rainfall events make it very easy to detect clogs, while others, especially ones with less intensity and duration, make things extremely challenging. We don't always know. Sometimes we need multiple rainfall events to actually conclusively tell if there is a clog. So back to the flagging system. To handle our rainfall QC processes, we needed to add a new flag type, and we call this climate good down here in the blue. So this handles the scenario where we cannot trust a 5-minute value, but we can trust the total that was represented during the time period impacted by the clog. The table shows a hypothetical example of where 1.2 inches fell in one given day, but it took several days for the water to make its way through the bucket. It is important to preserve these totals for climatological purposes, and a large part of the rainfall QC process is to understand when to trust and also not to trust those totals. So here's an example of our diagnostics page. This is what we use in real time and also historically to make QC decisions. So in this case, the diagnostics page detected a slow drip at our station in Northeast Maryland. You can see the yellow coloration at the top and the message next to it. The chart shown below with the classic slow drip signature confirms the presence of the partial clog. So I'm looking at that, I see an issue, then I look down here and look at what the actual trace looks like, and it overwhelmingly looks like a slow drip. Additionally, 2 other clogs were detected on this day back in April 2023. So at Harrington and Longwood, there were 2 just complete clogs. There were no tips through. Radar estimates, looking at radar data and spatial averaging confirmed that rain definitely fell there and we did not report it. The highlighted color shown kind of gives you an idea of the severity of what the actual QC test found. So red would be indicative of a higher chance that it's a clog, and yellow would be a lighter chance. Slow drips are harder to confirm, and that's why it's the lighter coloration in this specific case. In general, these tests, though, are designed to have high selectivity at the cost of generating false positives that can be investigated manually. So another element here is winter precipitation. It definitely adds a new dynamic to this process. Snow can fill the bucket and overflow, potentially resulting in missed precipitation. In certain scenarios, the mechanism can freeze, resulting in water moving through without being properly measured. So we use a variety of tools to handle these situations, including, again, radar estimates, cross-station comparisons, and by scrutinizing the signature of the data, as I showed you in the previous slide. In general, this results in flagging data at the county level because we have a lot of stations, and these types of issues can persist for several days, even weeks when we get a major snowstorm. So again, going back to the flagging system, we need to add a couple more flags. For better documentation, we add what I call the snow climate flag. It is the same as climate good, but it designates the reason for the flag is due to a winter precipitation event. And that's important to look at historically, especially when we're flagging 15, 20, 30 stations at a time. Likewise, the snow bad flag shown at the very bottom here indicates that the data cannot be trusted, just like the bad flag, and it's due to snow or ice. So in general, if we get more than 5 4 or 5 inches of snow, they're going to overflow the buckets, the tippers, and we can't trust it at that point. So adding all that together, historically, we've done all of this work historically, and this process has been applied for over 17 years of QC data. This resulted in identifying and addressing and flagging over 750 tipping bucket clogs and many additional issues such as sensor failures. In the earlier years of the network, there were many unexpected issues such as incorrect timestamps, parameters that were incorrectly labeled, and other issues such as irrigation around the station. So every year brought new problems, and using these tools was an excellent start to give us the flagged data to investigate further. So future QC development, it is our hope that the QC procedures we have in place will detect the majority of data issues. However, there is still much work left to be done. We are planning on leveraging our spatially dense network to detect issues such as sensor drift, shown in this graphic here as an example of where you have two sensors that are really close together, but in time they start to spread out. And that is very hard to investigate from a QC perspective, because at some point it becomes an issue, but you have to decide when that point is. Additionally, we want to better understand the sensitivity and selectivity of the current QC tests that we've run. We've flagged a lot of data, and we want to show, which tests work, how well they work, what are we missing, and just kind of summarizing all of that data. It's a lot of flagging data that we can process there. Finally, we want to use this information to better understand the characteristics of the stations in our network. We have a lot of data, a lot of unique stations, and I think it's important to kind of use these tests to help teach us something about our own network. So I'll leave you here with just a really cool animation of our network of an event that happened, I think it was 2018, so several years ago. So I will play this. This is animation of our dew points on July 9th, 2018. So just keep an eye out. Look for something interesting happening. And I think you'll see it there at the bottom in Sussex County with dew points dropping into the low 40s. And that was suspicious. Initially at that one station, we thought there was a problem and we were getting ready to flag it. But as the day went on, we were seeing that those low values spread to other areas in Sussex County. And then all of a sudden around now, it got worse. Dew points went down into the 20s, where it was in the 50s elsewhere. And it spread. And having these other stations here to support our individual values is very helpful, because everything was good. There were no data points here. This was just a very unique and rare feature where there's just this blob of extremely low dew points that kind of spread throughout the day. And it persisted for many hours and kind of faded away in the evening. We still do not understand why that happened, but it's neat to see it. And QC tipped us off to this unique feature kind of as it was happening in real time. That's all I have for you today. I appreciate that you took the time out of your day to listen to my talk, and I thank you for that.
All right, thanks, Chris, for that deep dive into all things QA/QC. At this time, we'll turn it over to Tina Callahan, who will go through any questions that are in the Q&A forum. Tina?
Thanks, Kevin, and thanks, Chris, for a great talk. We have, at this point, no questions that are in the Q&A. I'd be very interested to see, though, if anybody in the current audience has anything that they want to unmute themselves and ask. Please raise your hand using the raise hand tool at the bottom. Steph Baxter, you can go ahead and unmute, please.
Just put it in the chat, but are your data considered provisional for a certain period of time and then they become like the actual data? Or how does that work when you QA/QC? I'm just thinking of like the USGS stream gauges. Everything is considered provisional until the end of the water year, and then they go back and make sure that all the data are correct, and then they become actual data. So are yours considered provisional for any certain amount of time?
Yeah, so that's an excellent question. We don't have an official designation as far as when we truly finalize data. Well, at the moment, the way we're treating it is that we go in iterations. So again, we have immediate checks, we have checks that are done the next day, and then we'll have, if we discover that there's a sensor that has a problem, we need to look at that data retroactively, and in some cases, fairly rarely, would have to flag data. So I don't think we have kind of an official designation at that point, but we try to generally have data that's going to be permanent after a day or two and longer for rainfall, of course.
Okay, and then kind of as a follow-up to that, then, when you do see that there is a quality issue with the data, then do you go back and estimate what the data should have been? I mean, I don't mean like if the sensor's totally down and not functioning, but let's say you had a slow drip or the wind speed was off. Do you then go back and fill in the data gaps with estimates, or do you just leave them as no data?
Okay, so in the case of rainfall, we do not. I mean, we don't fill in any gaps, so to speak. We will go back and find kind of where we believe the problem started, and then where we believe the problem is finished. So in the case of a technician, going to a station and fixing the clog, and we'll just treat that entire time period as an issue, and we'll just look at it from the basis of the total rainfall that fell. And if we trust that value, then we'll flag it that way. And if we don't trust it, then we just say that entire time frame is bad data.
Great, thank you, Chris.
Thanks, Steph, for a good question. That's always something that we have to think about, is how people are viewing the data and how we can get to the right flagging. Anybody else have any questions? Keith, you can go ahead and unmute.
Yeah, thanks. Thanks for the presentation here. A lot of great ideas that we're rebuilding our anomaly report basically. So this is very timely for us. But I was wondering about with rainfall, if you guys use leaf wetness sensors. I don't know if you have those in your network, but we find them pretty handy for, kind of the using it in QA/QC for rainfall. If you're if you're not seeing rainfall, well, I guess it is a way to kind of point out periods of precipitation as well. Have you done anything like that?
So we don't have any active leaf sensors at this point, but we are looking into having weighing gauges, which of course could be very beneficial for winter precipitation. So I think that's the direction we're looking at least for some of our stations, to get a better feel for what's going on year round.
Thank you.
Sure.
That concludes our webinar for today. If you have any questions or things that you think of later, please feel free to reach out to us anytime at cema-info@udel.edu. Finally, just a reminder that we'll be having our third webinar next Thursday, September 26th at 1 p.m. Eastern. Our speaker that day will be Matt Shatley, and the topic will be Building Resilient Systems to Serve CEMA Data and Applications. If you haven't registered for that webinar yet, you can find the registration link at the original email where we announced the webinar series. You can also email us and we'll send you the registration link. Thank you again for your time and interest today. We'll hopefully see you next week.